before studying this triac as a light dimmer circuit, you should know the operation of a diac and a triac. All right. Now, I hope that you all are aware how does the SCR work. So, if SCR is unidirectional, triac is bidirectional. That's the difference. Okay. So, whatever SCR can do, triac can also do that, but at a lower voltages and currents. So let's say SCR can operate at around 1000 to let's say 5000 volts. Triac can operate in around let's say 250 to 500 volts. So it's used for medium power applications, not very high. All right. Now let us understand. So what does a light dimmer circuit do? Anyone before going to a topic as Triac as a light dimmer? So light dimmers are devices that are used to increase or lower the light intensity. So, there is a potentiometer over here, RP. So by changing this potentiometer, the light intensity of this lamp can be changed, right? So we will see the working in short. So in short, this is the meaning of your light dimmer circuit. Okay, you can increase or decrease the intensity of light just by changing this potentiometer RP. Now let's see how do we achieve this. Okay. So all of you are aware of diode characteristics, right? So diode characteristics, it's a bidirectional power device, a power switch, we can say. How does the diode turn on? Anyone? How does the diode turn on? What is the condition for diode to turn on? Anyone can go? So here I've plotted VI characteristics of a diode. So diode doesn't have any control gate. It doesn't have any control gate. So diode will turn on. See, it will start from zero, right? And you go on increasing the positive voltage. It is in the forward blocking mode. After it reaches a forward breakover voltage, which is around 25 to 35 volts, then the diode automatically turns on and its voltage across the diode reduces to a low value. So this is how the diode will turn on. Similarly, in the reverse direction also, when the voltages are negative, when the diode voltage is lesser than the reverse breakover voltage, then the diode will turn on in the negative direction also. So it's a bidirectional switch, right? It can turn on, it can turn off. All right. So, in order to turn on the diode, you should apply around the forward breakover voltage. It should cross forward breakover voltage. That means you require around 25 to 35 volts in the positive side and minus 25 to minus 35 volts in the negative side to turn it on. All right. So why I'm talking about bidirectional? Because AC is bidirectional. Okay, it has a positive half cycle, it has a negative half cycle. Now let us try to understand the circuit. Okay, so yeah, can you see this now, circuit? Can one of you reply quickly if the
Yes,
circuit
sir.
diagram is clear? Okay,
Yes, sir.
now look at the diagram carefully. Now, what will happen as soon as you apply 230 volts? Remember, you have applied 230 volts AC 50 hertz signal, single phase supply, and you have a AC lamp load. Okay, and then you have this circuitry, R1, RP, C1. This is C1, we can call it, right? Diac is there, triac is there. So how does the circuit will operate? How does the current will flow initially? So initially what will happen is, initially the lamp load will not turn on. This is my load. This lamp is my load, right? This will not turn on initially. So current will not flow to this. Why the current will not flow? Now that is the next question. Current will not flow through the lamp. So lamp will not glow initially. The moment we apply 230 volts. What's the reason for that? Yeah. Anyone? What's the reason for current to not flow? Okay. The reason is, so first case, we apply AC input 230 volts and you are applying it over here, but still the lamp is not glowing. The reason being is the triac is off. The triac is not conducting. Now, why the triac is not conducting? Because the diac because the voltage across the diac has not reached the forward breakover voltage. And how do we achieve that voltage? You achieve that voltage by varying this potentiometer. So let's say that this potentiometer is at the minimum position and you have just R1 and C1 connected in the circuit. So that particular voltage is not sufficient to cross the breakover voltage of the diode. So diode is also off. So in the first case, diode is off. Okay, triac is also off. So how will the circuit look like if these two devices are off? How will the circuit look like? The circuit will look like this. Let's name this point as A, B, and C. Okay. So the circuit will look exactly like this. The voltage across the track will be same as your V in because it is off. It is open circuit. The voltage across the bulb will be zero because no current flows. Here it is open circuit, right? So no current flows to the loop. All right. Here, if you see carefully, R1 and even if RP is almost at a minimum position, there will be a circuit formed by R1 and C1, but very minimum current flows through it. So that is insignificant. We can easily consider this scenario. So this is scenario is before firing of the diac. The triac is in the forward blocking mode. Okay. So what happens again? I repeat, the bulb doesn't turn on. It is off. Why it is off? Because triac is off. And why the triac is off? Because the diac is off. And why the diac is off? Because the voltage across the diac has not reached the forward breakover voltage. All right. So this is what will happen. All right. Before firing of the triac will be in the forward blocking mode or in the non-conducting mode. And the voltage across the bulb will be zero. Why the voltage across, I mean, the bulb will be zero? Because entire voltage will be spending over here. Entirely. It will go over here. Or V of triac input. So your triac voltage will be following the input whenever the bulb is off. Is this point clear to you? Then I'll proceed ahead. Why doesn't the current flow over here? Point clear? Yes, no, quickly tell.
No, sir.
No doubt, right? Or you have a doubt.
I have a doubt.
What doubt you have?
That I didn't understood the why the current will flow.
Current will?
Won't flow.
Because it is off, na? Triac is off. See, in this loop, you have this open circuit, right? Triac is off. See, this entire circuit, which is consisting of R1, C1, and diac, they are there to turn on the triac. If triac is not on, there is no meaning of the circuit at all. Are you understanding? All three,
Yes, sir.
all these together are working to turn on the diac, working to turn on the triac. But triac is only not on. So how will the current flow? Now in this loop, if I consider over here, the triac is off. Triac off means what? Replaced by open circuit. Now how will the current flow over here? Tell me in the open circuit case, right? So that's why
I don't know.
no current flows through the bulb. So bulb is off. Okay. Now what you do is, now listen what you do. Carefully listen now. Now you slowly increase RP value. To increase RP value means you increase the resistance. So now what will happen? Slowly and steadily, what will happen? The capacitor, there will be a RC time constant, right? The capacitor will definitely charge. And where it will charge towards the AC supply. So the capacitor will keep on charging, charging, and charging until it hits the forward breakover voltage. So let's say this forward breakover voltage is around 35 volts or 30 volts. All right. So at around VC1 has reached 31 volts or 30 volts, which is the triggering voltage of the diac. So now the diac has turned on, right? You have increased RP, and due to that, what happened? Due to that, what happened? Your diac has turned on. Whenever the diac turns on, what will happen? It will give the triggering pulses to the gate terminal of triac. So now triac will be turned on. And when the triac is turned on, it will be behaving as a short circuit, right? Again, I repeating, the circuit over here consisting of R1, RP, C1, and triac is there to turn on the triac. So when the diac turns on, the circuit will look like this. The bulb will glow because the current is flowing through the loop now. all right, and the voltage across the track will be 0. Why it will be 0? Because because it is start to work, right? So we are assuming ideal triac. So whenever the triac is on, it doesn't consume any voltage for itself, very very low voltage or 1 or 2 volt. So entire voltage appear across this bulb. Now tell me, this bulb is a AC load or a DC load? It's a AC lamp load. Okay, so it will turn on when we directly connect it to the 230 volts. See, we need not have this kind of a circuit scenario. We could have directly connected the lamp to the 230 volts AC supply. But why are we connecting this triac, R1, RP, C1, diac and triac, right? Because we want to control the intensity of the lamp. And how do we control the intensity of the lamp? By changing the value of RP. Now, let's say you increase the value of RP further. So what will happen then? Your diac will take a longer time to charge to reach that value because RC time constant has increased, right? So your alpha will increase. So when the alpha increases, what will happen? So triac will turn on after a further delay time. Alpha is the delay angle, right? So your triac will turn on after a later time, more later time. So that is what will happen. And accordingly, the waveforms you observe at the output are as follows. Did you understand this? After firing, how does the triac goes into forward conduction mode? Triac is just like SCR, working in both the positive and negative half cycle. Uh, yeah. So you understood how does the current starts flowing and the bulb is fully on now?
Yes, sir.
Okay. Now let's understand the waveforms. So this is my V in, that is very straightforward. V in is Vm sine omega t. Let me write. V in is Vm, capital Vm sine omega t. All right. So if you have a positive peak as Vm, negative peak as minus Vm, and over here this is the voltage across the capacitor. Now until it reaches breakover voltage of the diode, it will follow that voltage. And once it reaches a voltage across the diode, it will immediately go to zero and will stay at zero until the next half cycle continues. Okay. So it charges and instantly discharges. Sorry, your voice is echoing, so please keep it mute unless you are not talking. Okay. So the capacitor is charging. It will charge towards the supply, but where it will stop? It will stop when the diode has conducted. So as soon as the diode has conducted, it will apply the triggering pulses to the triac and the triac will turn on. So that's how the circuit will operate. So the more higher the value of RP, your alpha will keep on increasing and your conduction time for the triac will also keep on increasing. So triac will conduct for a shorter period of time. That means if triac conducts for a shorter period of time, your AC lamp load is also on for a shorter period of time. So next pulses are the gate pulses, the triggering pulses, which are appearing at the at this terminal. So what happens is the capacitor charges, but it discharges. It charges via this loop. See, the capacitor will charge via this loop through AC voltage. Once the AC lamp load is on, it will keep on, charging. And how does it discharges? It discharges via this loop. Okay. So when it discharges via that loop, it's instantly turned off. It instant turn off because the DAC almost has a zero. When they are on, when the power devices are on, their resistance is very very small. So the capacitor will discharge instantly. So here is what is happening. It is discharging instantly. So charging and discharging, and that is what is your gate voltage, which is applied at the DAC output, right? So this triggering pulses will act as a trigger pulse to the triac, and that will control the output, right? So now if you observe the output waveform, now I told you whenever the bulb is off, the voltage across the triac is V in. See here, in this period from 0 to alpha, let's say, the voltage across the triac is same as input, right? Whereas the voltage across the output is 0. So here you see the voltage across the output, that is here the load is actually your bulb load. Your bulb is the load, right? V out. V out. Where is the V out over here? I have not marked V out. This is V out. Okay. This is my V out. Plus, minus. This is my lamp load, right? So this is my V out. Okay. So whenever the bulb is off, the voltage across it is zero. So here it is zero. See? And when as soon as the triac turns on, the voltage across the triac is very minimum, so it's almost zero, whereas the output will follow the input, right, as it is. So here it is, your voltage across the load is V in, and the voltage across the triac is zero, and here it is exactly happening the same way. And the same thing will continue in the negative half cycle. All right, with respect to the negative pulses, your output voltage will be zero for that particular time. Your triac voltage will follow the input, and once it reaches the triggering angle again it goes to zero because the triac is conducting now, and the output voltage will continue to follow the input waveform. So these are all the input output waveforms for the triac as a light dimmer circuit. So did you understand the working of this? So tell me,
Yes,
anything
sir.
you want, anything you want me to repeat? Yeah. So this is a very important point which I want to discuss. When the triggering angle is zero, the conduction angle will be 180-degree. Meaning what? When the alpha is zero, your output waveform will conduct for full 180-degree cycle this way. Are you following? Right? This is the full conduction cycle. It will follow the full half wave period. It will conduct for 180-degree. But the load voltage will be maximum and equal to the input supply voltage. This is not possible over here because we are increasing the alpha. So as we increase the alpha value, theta will decrease. That means when you increase the alpha, your conduction angle, this is the conduction angle. See, this is, let's say if this is alpha, so from alpha to pi is my conduction angle, which is theta. So what is theta? Theta is pi minus alpha. Okay, theta is pi minus alpha. So as you go on increasing the alpha, the theta will go on reducing. And that means if theta is reducing, your load voltage will decrease, obviously, right? If you start your firing angle over here, let's say instead of this you start over here, so this will be zero, and this will be your load voltage, so very very small. See, so this red color one is the load voltage which I'm plotting for alpha very very high values. All right, so if alpha is very high, the conduction angle is low and the output voltage is also reduced. So that's how we control the output AC voltage. So alpha is controlled by varying the setting of the potentiometer, right? As I've told you in the circuit diagram, alpha is controlled by RP. So if we go on increasing the value of RP, you are increasing the, I've written one statement over here. So as your RP value is increased, the time taken for the capacitor to charge up to the breakover voltage of dioc will increase. So this will delay the trigger angle and therefore will reduce the conduction time. So this will cause the output voltage will reduce, right? So just by controlling the potentiometer RP, you can control the firing angle and you can decide when you want to turn on the triac. And that's the very crucial thing. Once the triac turns on, then the current starts flowing through the lamp load. So there are two major currents over here. Let me mark in green color. So when the lamp load is on and when the triac is on, when the triac is on, when the diac is also on, so majoritarily the current will flow from like this. Okay, from here to here. Okay, there will be a second current also flowing in these loops, but I'm not drawing it majorly. This is more important. So the supply will reach the load, lamp load, and it will start glowing. And now again you decrease the value of resistance. So what will happen? Alpha will reduce and the track will turn on earlier. So then the lamp load intensity can be varied easily. So this is in short the working of your triac as a light dimmer. Do you have any questions? Hello? Do you have any questions for this triac as a light dimmer circuit? It's very straightforward. These are the five waveforms which you have to draw. and explain the cases over here. I have not yet completed this write-up. I'll complete this and share it with you, most probably by today, after the lecture. So yeah, tell me if you have a doubt. You have understood thoroughly how does the triac work?
Yes, sir.
Okay, fine. All right. So now we go on to dual converter. Okay, let me be quick now. So you have heard of semi-converter, right? Semi-converter was single quadrant converter, meaning voltage and current both cannot reverse. They are in the positive. They are both positive. Then we had fully controlled converter. We call it as a full converter. It's a two quadrant converter. Here the voltage can be reversed, but current cannot be reversed, as you can see from here, right? Voltage can be reversed, voltage can be positive or negative, but current cannot be negative. All right. So we have a dual converter. Now, what is a dual converter? This is one node actually which I'm using, so I cannot mark anything over here, but it's fine. A dual converter is a four quadrant of operation. That means over here we can have voltage and current both can be positive or negative. So as you can see from the quadrant, it's a four quadrant operation. So you can have alpha 1 or alpha 2 less than or greater than 90 degree. So I will explain what do you mean by alpha 1 and alpha 2. But here the current and voltage both can be reversed. That means you can operate this dual converter in any of the quadrants, either in the first or second or third or fourth. All right, did you understand what is a dual converter in principle as comparison to semi converter and fully controlled converter? Any doubts in this?
No, sir.
Okay. Okay, so this is the dual converter. You remember the half circuit we have studied. I mean T1, T3 and T5, T4, T6 and T2. You have studied as a three-phase control rectifier, right? In a dual converter, we have other set of converter, converter 1 and converter 2. So converter 1 you are familiar. So here we are calling it as T11. It's a first converter, so we are calling it T11, T13, 15, 14, 16 and 12. The sequence should be remembered. Okay. Next, we are applying a three-phase supply. So we have three phases A, B, and C. So VAN, VBN, and VCN. The same supply has been applied to converter number two. But in converter number two, the connections are made in such a manner, that the SCRs are opposite. The SCRs are connected in reverse fashion as compared to converter number one. Okay. So here we have T21, T23, T25, T24, T26, and T22. 2 stands for converter 2 first, and the second one is the numbering of the SCR. So here in between we have connected a motor load, right? We can have a DC motor as a load, right? So this converter will provide the voltage across, output will be VD1, and here it will be VD2. Here I have not written the direction properly. We'll come back to it. Here I've written both as plus, so that's not correct. One of them has to be negative. So we will decide at the end which one is negative. So here this point we are calling it as X and this point we are calling it as Y. Remember, we have a three-phase control rectifier as converter number one and three-phase control rectifier as converter number two with reverse direction of SCRs. Okay, and the supply voltage is applied to both. I mean all three of them. I mean both the converters. So we have three pairs, three legs, 1 and 4, 3 and 6, and 5 and 2. Here also 1 and 4, 3 and 6, and 5 and 2. So let us see the working of it. Okay, fine. Now let us decide what will be the firing angle. So we want the average value of VD1 to be equal to VD2. So here it is the VD1 and VD2. Output of converter 1 is VD1 and output of converter 2 is VD2. All right. So for converter 1, we have already derived it for a three-phase control rectifier. VD1 will be given by 3 Vm by pi cos alpha 1. Okay, where Vm is the peak value of the line voltage, where alpha 1 is the firing angle. Similarly, for converter 2, VD2 will be minus 3 Vm upon pi cos alpha 2. Right. Why it is minus? Because it's connected in the reverse, and I guess probably this is negative. Oh, sorry. Yeah. So this is the polarity it provides. It provides a reverse polarity. That's why we have a minus sign over here. So VD2 will be minus 3 Vm upon pi cos alpha 2. Now, from where we got this formula? We got this formula while discussing the three-phase control rectifier. So you can refer that thing. Okay. So what do we want? We want the average value of VD1 and VD2 to be almost equal, right? So that means VD1 average should be equal to minus of VD2 average. All right. And here, if you add these two voltages together, what you will probably get is that cos alpha 1 plus cos alpha 2 will be equal to 0. Rest all the terms will go on the right hand side because all the other terms are same. So they will cancel out. So cos alpha 1 plus cos alpha 2 is equal to 0. That means cos alpha 1 is equal to minus of cos alpha 2. And that you can write it as cos of 180 minus alpha 2. Right. So if you substitute it over here, you will get alpha 1 plus alpha 2 is equal to 180 degree. Are you following? Or else we can say alpha 1 plus alpha 2 is equal to pi. That means if converter 1 SCRs are fired at 70 degree, converter 2 SCR should be fired at 110 degree. Did you understand this concept? Together, it should be 180 degree. Alpha 1 and alpha 2 should be 180 degree. So alpha 1 is associated with firing angle of SCRs in converter number 1, and alpha 2 is associated with firing angle of SCRs in converter number 2. All right. So if the converter 1 firing angle is 70, other one should be 110. So if converter 1 firing angle is 40 degree, what should be the converter 2 firing angle? Converter 1 is 40. What should be converter 2 firing angle? Total should be 180.
140.
Yeah, correct. Exactly. 140. Absolutely right. So both the converters are fired simultaneously, but at different firing angles. That means some of the SCRs in converter number 1 are fired at 70 degree, and in converter number 2 they are fired at a different firing angle. That's the difference. Okay. So let's proceed forward. So remember, whenever we have studied this, right, in a three-phase control rectifier also, or in a single-phase control rectifier also, whenever alpha is greater than 90, your VDC will reverse. Why VDC will reverse? Anyone can tell me? Anyone remember something? Why VDC reverses? Yesterday I talked about it. See, here I have explained. This is alpha. This is alpha. I mean, I'm just taking an example over here. This diagram which I've drawn is for alpha less than 90 degree. So here you see more positive half cycle, right? Positive is more. VDC is positive, meaning average value of the output is positive. But what if the firing angle is like this? Let me draw it and show it to you. The firing angle is very much greater, like this. So what do you observe over here? Okay, you observe a major portion of negative half cycle, and the positive part is very, very less. So average value of output will be negative. Are you following what I'm saying? What I'm trying to convey? I'm trying to convey is that if my alpha is greater than 90 degree, my VDC will reverse, but IDC will not reverse. That means my VDC and IDC product will reverse. That means my power will flow from DC side to AC side. Normally, how the power should flow AC to DC. But if my alpha is greater than 90 degree, my power will flow from DC to AC side. So this is my DC side. It's a rectifier, right? So it will convert AC to DC. So across the motor, V out will should be a DC voltage. So in case of alpha greater than 90 degree, the power flow will be from DC to AC. Okay, from DC back to the grid. So this you have understood. Okay. Remember we have drawn this. I'm not explaining this again. How to draw this, line voltage and all that. We have all discussed this together. Alpha 1 equal to 60 degree case. Alpha equal to 60 degree case. How will be VD1 and VD2? See, this is how the VD1 and VD2 will be. Okay, so this is the VD1 voltage, converter 1 output, and at the same time, if alpha is 60 degree, alpha, of converter 1 is 60 degree, what should be converter to alpha? If converter 1 alpha is 60 degree, what should be converter to alpha as? Tell me. Hello. It should be 120, right?
180.
Why 120? See, though these two together should be 180, na? This is converter 1 output, this is converter 2 output. Alright, so this is what will happen. So you need to figure out how we got this waveform. It is similar to figuring out the waveform for a three-phase controlled rectifier, and we have already discussed for the case of 60 degree. Only thing is you have to follow for how do we got the waveform for 120 degree. Now I am not explaining that right now right away, but this is how the waveform will look like for 120 degree. Now what do we want? We want average value, right? So what do we want is we want VD1 equal to VD2, right? So this is what do we do is we reverse this VD2. So if you plot minus VD2, how it will look like? It will look like this. It will go below. All right. So from the waveform, it is clear that the average value of VD1 and VD2 are same. If you see carefully, average value of VD1 and VD2 are same, but the instantaneous values are not same. Are you agreeing to this fact? Both the waveform VD1 and VD2 are appearing to be average wise similar, but instantaneous values are not same. Okay, so there is a problem now. That is why we connect point X and point Y. That is a positive output point of converter 1 and positive output 1 of converter 2 directly. So if we connect it together directly, there will be a huge current circulating through the two converters, because the instantaneous values are not same, right? The instantaneous values are different, right? Even though they are average value is same. So what will happen is if you connect this as it is directly, there will be a huge current circulating in the circuit. Okay, so that will be not good at all for the SCRs, neither for the dual converter. So what you do is you connect a reactor over here, VL, I mean inductor. Inductor has a resistive coil also. So between X and Y, you connect a reactor like this. So now this is what it will do. Let's understand that now. Is this clear to you? Why we connect the reactor? Because instantaneous values of both VD1 and VD2 are different. That's why at that one point of time, there will be a huge current flowing into the circuitry and that will damage the SCR itself. That's why we connect this L. So L, what the L will do? It's a current limiting reactor with a small resistance. Reactor means inductor. So with this reactor, your slight increase, inductor doesn't like current to change rapidly, right? So your di by dt will be minimized. Inductor is always going to minimize di by dt of your SCR. So let's say there is a sudden change in the voltage. So suddenly there is this, large ingress of current. Okay, large current is flowing through in the circuit, and without this in a inductor, it will what this inductor will do? It will not allow the sudden change in current, right? So hence it will prevent that thing to happen. And this with this reactor, your di by dt will be reduced, and also the small resistance will reactor will minimize the current circulating in the dual converter. So that's for the safety purpose. We connect this small reactor or inductor, okay, in between. Now let's understand the working for alpha less than 90. So alpha less than 90, the converter will operate as a rectifier, or it is also called as motoring operation. That means the power flow will be from the supply to the load. The power flow will be from the supply to the load. And here the VA value of the output of the converter is given by 3 root 2 Vm, 3 root 3 Vm cos alpha upon pi. This we have derived for three-phase control rectifier, right? For alpha less than 90 degree, this is the formula. So over here, what do we have? We have VA voltage greater than the, what is EB? Back EMF of the motor. So VA voltage will be greater than EB. So the power will circulate from the supply to the load. Okay, so power flow is from AC to DC. Now, if you keep alpha greater than 90 degree, what will happen is for alpha greater than 90, output voltage will be negative. All right. So your magnitude of your this back EMF will be greater. So here you have a reverse armature connection. As you can see, reverse armature connection. Have you heard of this question that can rectifier, controlled rectifier work as a line commutated inverter? Yes, it can. It can work as a line commutated inverter under the circumstances that your alpha is greater than 90 degree and your back EMF is reversed. So here we have a reversed armature connection, and in this case, your power flow is from DC to AC. It's going from the load to the source. We have discussed enough about this before, and this mode of operation is called as inverter or regenerative operation. So you have two modes of operation: alpha less than 90, alpha greater than 90. And in case of dual converter, one converter works in the rectification mode, other converter works in the inverter mode always. Is this okay? Yeah. Now, when we add them together, what do we get? VD1 plus VD2, VD1 minus VD2. Let's say the converter out VL. What will be VL voltage now? Where is VL now? Ah, this is VL, right? What will be VL voltage? It will be VD1 minus VD2. Is it not? Yes or no? Will it be VD1 minus VD2, right? So let's plot the voltage across the reactor, inductor. So this is how the voltage across the inductor will look like. It's VD1 minus VD2. You can cross it, you can check it out. And this is how the waveform will look like. And the current will always be positive. This will be the current flowing through that reactor, IL. And yeah, this is the theory. We have seen that. So net voltage across the inductor will be zero, net voltage. Okay. Instantaneous voltage will be there. So VL is L di by dt. So if in order to plot IL, when VL is positive, we have increase in IL. And when VL is negative, decrease in IL. And that's how we plotted this, right? Whenever we have a decrease in voltage, your current will decrease like this. So that is how we have seen. So converter 1 current is a steady state load current IL plus I load, and your converter 2 current will be help in making sure that inductance circulating current is going back to the three phase mains. Meaning, if you have this converter, if alpha 1 is less than 90, alpha 2 is definitely greater than 90, right? So over here, the power is flowing from AC to DC, and for the converter 2, the power is flowing from DC to AC. Are you understanding? So the power is going back to the grid. Again, I repeat, for converter number 1, alpha 1, let's say it's 60 degree. So converter number 2, alpha 2 will be 120, right? That means converter 2 is operating in the inverter mode, and converter 1 is working in the rectifying mode. That means converter 1 is converting AC to DC, and converter 2 is converting that AC back to AC again. So the power flow is like this: converter 1 power flow is AC to DC, converter 2 power flow is from DC to AC. So whatever you are supplying, you are getting it back, right? So that's the beauty of dual converter. So in the dual converter, both the converter has dual roles. If one converter works as a rectifier, mainly that is the source of power, then the other converter will work as a line commutated inverter. Takes over the operation if regeneration is required. Okay. And if a load is a DC motor drive, let's say VD1 and VD2 is 220. So back EMF is, let's say, 210 volts. So in order to bring down the speed of the DC motor drive by braking, converter 2 is already working as an inverter, let's say. So to bring down the motor into regenerative mode, alpha 2 can be changed from 120 to 110, say. Okay, such that VB2 will be less than EB, that's the back EMF. And when VD2 becomes less than back EMF, your current IL load and IL will start to flow through the DC motor drive into the converter 2. So then the converter 2 transfer the power from the machine and transfer it back to the three phase mains. Okay. In this case, your converter 1 is not supplying much power. Your converter 2 has taken charge of the operation. So just by adjusting the firing angle, your armature current is reversed in millisecond times. So that means I can immediately control the speed of your, a DC motor like this. So as converter 2 feeds back the power to the three-phase AC mains, speed of the AC drive motor drive will reduce, right? So let's say from 1500 RPM, it will go to 1200 RPM. So it will release its kinetic energy, right? So as the speed comes down, you have to readjust the firing angle as per the requirements, all right? So that is how the dual converter will help you in applications of control of speed control of DC motor. But if they are not asking much in details, you don't have to go over here. This is an example which I'm giving. So from point number 15, it's extra. If they ask you explain the application of dual converter, then you write whatever is written after point number 15. Or before that, till point number 14, the explanation is enough. Okay. Yeah, so that will be it for the dual converter side. Just one thing you remember, it's a all the four quadrant operations are possible over here. And what is alpha 1 and alpha 2? I've already explained that. And why we require a reactor over here? We require a reactor because there can be a huge amount of current flowing through the load, right? So to prevent that, we connect an inductor. So in this case, converter 1 can act as a rectifier mode, then converter 2 will act as an inverter mode, or converter 1 can act as an inverter mode, or converter 2 can act as a rectifier mode. Anything is possible. Okay, so that will be it for the dual converter part with the waveforms. Anything you want to ask? I know it's a little bit tough topic, tougher than your whatever you have seen. That's why I kept it at the last. So up to you whether you want to keep it as an option or you can have to go through it. You will study it. Fine?
Yes, sir.
Let me turn off the recording.